everyone. In this video we will learn about the valence shell electron pair repulsion model, or the VSEPR model. When we want to draw a molecule, we have to care the electron pair surrounding an atom in the molecule. Why? Because the electron pair, they tend to repel each other, and the shape of the molecule is the result of this electron pair repulsion. This is the VSEPR, or the valence shell electron pair repulsion model. This is what it states, and the model portrays bonding and non-bonding electron pairs as occupying specific positions around the central atom. Like here, as you see, this is the drawing of ammonia molecule according to Lewis. This is the non-bonding electron, we call it lone pair, and these are the bonding electrons. So these are the bonding electrons. We will get in touch with the following terms. Electron group geometry indicates the arrangement of bonding and non-bonding electron around the central atom without differentiation, as we can see here. So here we have as electron group geometry 4. Also, we will get in touch with the following term, molecular geometry. This molecular geometry indicates the arrangement of atom around the center as a result of electron pair repulsion. So caring about the electron pair repulsion. We will explain in this lesson in details this table. This table is very important because it will show us how to count the electron groups, bonding groups, lone pairs, electron geometry, molecular geometry, approximate angle, and examples. So we will take examples that they are listed in the table, but all examples that they are similar will be the same. We will start one by one. I will explain all this table. We will start by the first row by taking example CS2. So I have this molecule, carbon disulphide. First of all, I have to draw it according to Lewis. So Lewis structure before knowing its geometrical and molecular shape. According to Lewis, carbon belongs to group 4. So it has 4 electrons in the valency. And sulfur belongs to group 6. It means that it has 6 electrons in the valency. Now, C is the central atom because, as you see, it has the lowest subscript. So I start by drawing single bonds. And then each one should reach its octet in order to feel that the satisfaction. So first of all, let me also calculate the valence electron, which is 4 plus 2 times 6, which is 4 plus 12, sum up to 16 electron. Carbon should feel 8 around it. This is 1, 2, 3, 4. I will continue either by adding lone pairs or adding bonds. Carbon, it doesn't have lone pair, so I will start adding bonds. So 1, 2, 3, 4, 5, 6, 7, 8. Now carbon is feeling 8 electrons. It means it reached its octet. Sulfur also should feel the same. So 1, 2, 3, 4, 5, 6, 7, 8. Because sulfur can occupy or have a lone pair. Now, if I count these electrons, should be 16 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this is how I draw it according to Lewis. Now I will start answering step by step the table. This is the drawing. Electron group, I will answer the electron, in which electron group it is, and then the bonding group. We will answer all these things. Lone pairs, and then electron geometry, and then molecular geometry, electron geometry, and then molecular geometry. We will answer all this for this molecule to know exactly the shape and the angle it makes, and then the approximate bond angle. So the approximate bond angle. Okay, let us start one by one. What is the electron group around the central atom? Electron group around the central atom, we think of this as one group and this as one group. Despite if it's double or single or triple, we call it one group. So we have two groups, 1 and 2. So electron group 2. Bonding group also, this bonding and this bonding. So two groups. Lone pairs, no lone pairs on carbon, so 0. Now, electron geometry, it is linear. Electron geometry, it is linear. Why linear? Because they form two electron groups or bonding groups. And according to VSEPR, the maximum to be away from each other to be linear. So this we can think of it in the form molecule of AX2. A represent the central atom, which is in our example the carbon, and the X represent the sulfur here. So electron geometry is linear, molecular geometry also linear. Approximate bond angle for the linear, the approximate bond angle is 180. So now we can memorize these general things to apply on any example. This is one example, but any example that follows the general formula AX2, which has a central atom surrounded by two atoms having electron group 2, bonding group 2, and lone pair 0, the electron geometry will be linear and the molecular geometry also linear, and the approximate bond angle is 180. Now let us move to the second example in the table in order to explain it. The second example given in the table is BCl3. Let us first of all, as usual, draw it according to Lewis. First of all, the valence electron. Boron belongs to group 3 and chlorine belongs to group 7. So the valence electron 3 plus 3 times 7, the bond, the group, which is 21 plus 3, 24 electron. Now let us draw it according to Lewis. Boron surrounded, first of all we draw the single bonds. Okay, first of all, till now we don't know the angles, so students can draw it anyhow. Students maybe draw it like this, no problem. Later on we will see exactly the molecular geometry and the bond angle corresponding to it. Boron belongs to group 3, so these are the 3 electrons. This has exception to the octet rule. It is sub-octet rule because the boron cannot form more than 6 electrons, so cannot fill more than 6 electrons. So this is exception to the octet rule. Chlorine, no exception, should fill 8. So 1, 2, 3, 4, 5, 6, 7, 8. Similarly for the rest of chlorine. If I have to count these electrons, 6 by 3, 18, 19, 20, 21, 22, 23, 24, it means that the distribution is correct. So each Cl fills 8, reaching octet. Boron, as we said, it is sub-octet because it cannot fill 8 due to its position in group 3. Maximum it can fill 6 electrons. Now let us answer the questions here according to the molecule that I have. What is the electron group? So the electron group around is, let us see, this is 1, 2, and 3. So electron group is 3. Bonding, also bonding electrons 3. So 3. Lone pairs, no lone pairs on the boron, so 0. Okay, electron geometry. What is the electron geometry for this? According to VSEPR, since we have no lone pairs here, the maximum that these be away from each other to minimize the repulsion of electrons, it should constitute the geometrical shape, which is trigonal planar. Trigonal planar. So if I want to draw it, it should be like this, such that to minimize the repulsion between the electron pairs. So this is the maximum that could be away from each other. So the molecular geometry also trigonal planar, and they have angle 120 away from each other. Now we can generalize any molecule in the form of AX3. A is the central atom in our example boron, and Cl is the other atoms. Any molecule in this having this general formula, they have trigonal planar shape, electron and molecular geometry, and the angle is 120. Now we will move to another example and see what molecular and electron geometry they can make and the angle. I'm following you always as you see the table examples, but definitely these examples apply on any molecule. That's why I'm writing for you at the end the general formula. Now we want to take SO2. Let us take SO2 example. As usual, we will draw it according to Lewis. Sulfur belongs to group 6, so it has 6 electrons in the valency, and oxygen belongs also to group 6, so also it has 6 electrons in the valency. Lewis structure, we have sulfur as the center. We start by single bonds, and let us see how to distribute. So we have to calculate the valence electrons, 6 plus 2 times 6, which is 18 electron. Okay, let us start drawing Lewis structure. Sulfur 1, 2, 3, 4. So we have to add more, because the minimum for sulfur to feel 8. It can feel more than 8. It can be an exception to the octet rule due to the fact that it is in period 3, and any elements in period 3 and down, they can exceed Lewis because of the MTD orbitals. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Till now like this. I will continue. Oxygen cannot exceed Lewis, so should feel 8. 1, 2, 3, 4. It can make lone pair. So 5, 6, 7, 8. Similarly for this oxygen. Let us count the electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Still 2 electrons missing, so I will put them as a lone pair on sulfur, because as we said, sulfur can exceed octet, so it can feel more than 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, no problem. It can feel, because as we said, it is in period 3, and in period 3 and beyond, the atoms can exceed the octet and feel more than 8. Now let us answer the questions. Electron group, let us see, this is 1 group, this is 2 group, this is the 3rd one. So electron group is 3. Bonding only 2, because lone pair is non-bonding. We have here on the central atom 1 lone pair. So according to this has general formula AX2E, where A here represents the central atom, here in our example sulfur, X represent other atoms, in our example oxygen, and E represent lone pair. and E represent lone pair. So here, as you see, 2 and 1, which means that there is one pair of electrons, as if 1, 2, 3. So the electron geometry as 1, 2, 3. But the molecular geometry, the molecular electron group 3, but the molecular, it's not trigonal planar, because as you've seen in the first example, AX3, when we spoke about AX3, the geometry, molecular geometry, it was trigonal planar. But here, instead of one bond, it got substituted by lone pair, which have more electron repulsion effect. So the angle will be less than 120. The angle will be less than 120. So the electron geometry, like AX3, which is trigonal planar, but the molecular geometry, how it looks in space, it won't be trigonal, it will be bent. It will be bent, and the approximate angle will be less than 120 degree. Why less? Due to the substitute here in this example of one bond by lone pair. So the effect of lone pair makes it bent. So angle will be less than 120. So as you see here, it is 3, as we said, and the bonding group 2, lone pair 1. Electron geometry 3 around it, which is trigonal planar, but we said the effect of lone pair makes it bent and the angle less than 120. So if I want to draw it correctly according to the molecular geometry, I will draw it bent in structure. Why bent? Because again, instead here of bond, it's substituted by lone pair. So we can generalize that any structure in the form of AX2E, it has bent shape and it has angle less than 120. Now we will move to another example in the table to explain. Okay, so the other example here that we will talk about. Now we discussed this one, we discussed this one, we discussed this one. We will move into this one, CH4. As usual, we will start by drawing Lewis. So if I have CH4 molecule, carbon belongs to group 4, so it has 4 electrons in the valency. Hydrogen belongs to group 1, so it has 1 electron in the valency. If I want to calculate the valence electron as per Lewis, so it's 4 plus 4 times 1, which is 8 electron. Okay, this is the central atom, carbon, and surrounded by 4 hydrogen atoms. Hydrogen should feel around it 2 as per do-it rule. So 1, 2, okay, 1, 2, 1, 2, 1, 2. Carbon should feel 8, no exception for carbon. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and it's the same valence electrons. So this is the correct way for drawing Lewis. Now let us answer the following question. Electron groups 1, 2, 3, 4 around the central atom. Bonding, also all these are bonding. Lone pairs, no lone pair on the central atom, 0. So any molecule in the form of AX4, A is the central atom in our example carbon, X is hydrogen in our example the other atom. Any molecule in the form of AX4 according to VSEPR should have tetrahedral structure. It's the maximum, because when they are distributed in tetrahedral structure, the electrons are away maximum from each other to avoid to minimize, you cannot avoid but to minimize the repulsion. Molecular geometry also tetrahedral, because no lone pairs. When no lone pairs, electron geometry like molecular geometry. And in tetrahedral, approximate angle 109.27 degree. So the correct way of drawing it is like this, which is the shape of tetrahedral, and the angle here 109.28 or 27 degree. Okay, so 109.5 here as per the example. So take this as 109.109.5 degree, the angle as in tetrahedral. So we discussed this example. Now let us move to another example, which is pH 3, and see how we will answer the following questions. So let us see how we'll answer the following questions as per pH 3 molecule. Okay, pH 3 molecule, as usual, let us first of all draw it according to Lewis. Phosphorus belongs to group 5, so it has 5 electrons in the valency. Hydrogen belongs to group 1, so it has 1 electron in the valency. Let us count the valence electrons for the molecule, P5, and 3 times 1, so 8 electrons. Okay, according to Lewis, this is the central atom, phosphorus, hydrogen, hydrogen, hydrogen. Okay, phosphorus, hydrogen follows the duet rule, so okay, it's feeling 2, but phosphorus should feel 8. So 1, 2, 3, 4, 5, 6, so still it needs this lone pair. And if you add these electrons, sum up to 8 electrons, which is correct way of drawing Lewis. Now let us answer the questions related to it to know eventually its molecular geometry and the approximate angle. Electron group, we have 1, 2, 3, 4, so 4. Bonding, the bonding 3. Okay, so 3. Lone pair 1. Okay, now electron geometry, you think of it as the previous one, AX4, because there are 4 group, and we said when it is surrounded by 4, it has the shape of tetrahedral. This molecule in the form of AX3E. So A here in our example is phosphorus, X hydrogen, and the 1 lone pair, which is this one. But according to molecular geometry, as we said, here the bond that was in CH4 replaced by lone pair, which has more effect. So it squeezes more the bonds, so the angle it will be less than 109.5 degree, because it's not exactly like CH4 as if surrounded by 4 bonds, and the molecular geometry, it will be trigonal pyramidal. Trigonal pyramidal. So any molecule in the form of AX3E, it will have molecular geometry trigonal pyramidal. So this one done. Let us move to H2S. Let us see H2S. Again, we will answer all the questions related to this molecule. Okay, now we have H2S molecule. Let us see how we will draw it. First step, according to Lewis, sulfur belongs to group 6 and hydrogen belongs to group 1. If we want to calculate the valence electrons, so 2 times 1 plus 6, sum up to 8 electrons. Sulfur is the central atom. Hydrogen feeling 2, okay, sulfur should feel 8. So 1, 2, 3, 4. Sulfur can have lone pair, group 6, so I add 2 lone pairs. Now if you check the electrons, they will sum up to 8 electrons, which is correct number. Now let us answer the questions. Electron group, we have 1, 2, 3, 4. So according to the electron group, we have 4. Bonding only 2. And we have here 2 lone pair. So the effect of lone pair is high. For electron group 4, the electron geometry is tetrahedral, as you've seen. But because here, tetrahedral, yeah. But because here, instead of 2 bonds replaced by 2 lone pairs, the bond will squeeze more and more. So it will be bent in shape, and the angle less than the one in tetrahedral, which is 109.5. So if I want to draw it correctly, according to VSEPR, it should be drawn like this in the bent shape. So we can say that any molecule in the form AX2, and here 2 lone pairs, so we write E2, it has bent shape and the angle less than 109.5. Okay, we will move to the other example, which is PCl5. And also we will answer all the questions. Okay, another example, which is PCl5. So first of all, we will draw it according to Lewis. Phosphorus belongs to group 5 and Cl belongs to group 7. P, and there exists 5 Cl around it. Okay, phosphorus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, no problem, because as we said, any elements in period 3 and beyond, they can exceed Lewis. Chlorine cannot exceed Lewis, should feel 8 around it, so 3 lone pairs and 7, 8. So each chlorine 3 lone pairs and feeling 8. If you count the electrons, you will find them like the valence electron, which is 5 plus 7 times 5, which is 40 electrons. So this is Lewis. Now let us answer the questions. Electron group, let us see the groups around the central atom. 1, 2, 3, 4, 5. Bonding also 5. No lone pairs on the central atom. So this molecule in the form of AX5. Any molecule in the form of AX5 to have electron geometry, it will be trigonal bipyramidal. Trigonal bipyramidal. Trigonal bipyramidal. Also, its molecular geometry, because of no lone pairs, like electron geometry, which is trigonal bipyramidal. What is the approximate angle in trigonal bipyramidal? Let me show you. In trigonal bipyramidal, the equatorial, these are the equatorial, they have angle 120 degree. And the axial, these are the axial, they have 90 degree. So equatorial like this, and this 90 degree. So in this example, as we see, we have, so this is trigonal bipyramidal. So here the angle is 120 degree and here the angle 90 degree. Now let us move and discuss another example and answer all the questions to know the molecular and geometrical shape eventually. So this is till now done from it. Now let us move to SF4, this one. Okay. SF4, first of all, according to Lewis, if we want to draw it, S belongs to group 6, so 6 electrons in the valency, and fluorine belongs to group 7, 7 electrons in the valency. Valence electrons, 6 plus 4 times 7, 42, so 48 electrons. Let me start drawing according to Lewis. So S, and it is surrounded by F4F. F cannot exceed Lewis, so should feel 8, so 3 lone pairs and 2 bonded, 1, 2. Similarly for the rest of F. If you count these electrons, 6 by 4, 24, 25, 26, 27, 28, 29, 30, 31, SF4, let me see, I'm drawing SF4, yeah, okay, 6 plus 4, wait, there is mistake, yeah, 6 plus 4 times 7, 4 by 7 is not 42, it's 28, okay, 28 and 6, it sum up to 34 electron, okay. So 6 here electrons by 4, 24, 25, 26, 27, 28, 29, 30, 31, 32, and still we need 1 lone pair to sum up to 34. This is the correct way for Lewis. Now, electron group, let us answer the questions. Electron group, we have 1, 2, 3, 4, 5. Bonding, we have 4. 1, 2, 3, 4. This is the bonding. Lone pair, we have 1. So when the electron group is 5, the electron geometry, as we've seen before, it is trigonal bipyramidal. But because here, as you see, one of the bonds substituted by electron, so it will squeeze more the bonds and will have a seesaw structure like this one. Seesaw, and let me show you the angles. Okay, like this one, seesaw structure. It's drawn like this, as if here one child is sitting, one child is sitting, as this is the base. Now let me show you the angles. The angles in the equatorial should be less than 120, and the axial less than 90 degree. Now let us move to another example, which is ClF3. Okay, in order for you not to get bored, all of them you draw them as I've showed you, and you answer the questions. When you have 2 lone pair and you have 5 electron group, but 2 lone pair, the shape will be T-shape and the angle less than 90 degree. When we have 3 lone pair, it will be linear as this one and the angle 180. If now we have electron group 6 and no lone pair, the shape octahedral and all the angles 90. If instead of 1 here bond substituted by 1 lone pair, it will be square pyramidal like this one. And if it's substituted by 2 lone pairs, it will be square